So let's look at TR of 3, tree of 3, by this definition of tree. And again, there's some variations, like the one you'll find referred to in the Wikipedia article on Kruskall's tree theorem is slightly different. It talks about labeled trees, but this one is from the Friedman reference that's referenced in that article. So k equals 3. By one of our earlier facts, it's silly to start with just like a single branch or a double branch, and so we might as well start with a triple. Now, unfortunately, what that means is we can never use a triple branching again, because anytime in a bigger tree, if I ever see a triple branching, then I can just take this guy, that's t less than or equal to 1, of any tree that's built off of this, and I can just put it at the triple branch. So it's a little bit like n of 3, where that third number that you put in isn't necessarily that useful in itself. It just breaks the logjam for making it more useful to use 1 and 2. So here, this is just going to make it possible to ever do a double branch. Because remember, if the first little guy was a double branch, it basically made it impossible to use a double branch ever again. So now I can do basically binary trees with a bit more flexibility. Okay, and that's going to be crucial. Okay, so that's legal, obviously, because there's only t less than or equal to 1. There's nothing else. You could just then do something simple. Now, I can't extend every leaf, as we said before, but I could do something fairly simple, just extend one of them by 1. Okay. Now, if I wanted to further extend that, if that's all I did up through the 2 level, and I wanted to further extend that, well, I would be extending every leaf. So this isn't very smart. This is a dead end. So it's legal, but it's a dead end. So it's not that interesting to investigate if we're trying to figure out, can we make enormous trees out of this? Okay, but it's good to think about. Okay, so we want to keep branching, basically. Okay, I'm never going to extend all of these. So basically, at any stage, one of these is going to be dead. Okay, and that's fine. Okay, so we could then maybe just branch this guy, binary branch, a binary tree. Okay, so that'll be legal, if only because these 3 can't get mapped to these 2. So remember, just to remember how it works, that's t less than or equal to 1, and I'd like to know, could I map those into the only other subtree that's interesting here, t less than or equal to 2, so that the front rank of here goes to the front rank of here, and all common ancestors go to common ancestors. It's inf preserving. Well, for the very simple reason that there's 3 things here and there's 2 things here, I can't do that. Okay, so that's definitely legal. Okay, so let's go ahead and try to extend this a bit more. What if I tried to go ahead and maybe double branch this guy? Okay, well, that's not going to be legal. Okay, here's the deal. Here's t less than or equal to 2. And the whole thing is just t less than or equal to 3. Okay, so I could find a match by taking all of this stuff up through the 2 level and mapping it to the whole tree, if I can find a way so that this front rank here, this is t2, just the 2 here, maps to the front rank of t less than or equal to 3, in other words, t sub 3. Okay, and so that it's an embedding, it's 1-to-1, and inf preserving. Well, why don't I just not mess with the root? Can't mess with the root, and not mess with the triple branch. It's pretty hard to mess with the triple branch because it's so special. But that's okay, leave it. And then just slide this guy, this triple, down to here. Okay, then that's just totally going to work. This guy goes to here, this guy goes to here, this guy goes to here. That's totally a match. Okay, so this idea of taking part of one of the branches and sliding it down and matching it in, that's the kind of match that we're trying to avoid. So this is not legal. We have dead-ended ourselves, basically, into having a match, which we don't want. Okay, so let me show you something that does go a bit further. I'm not going to go into gory detail here, mainly because I haven't figured out the rules for the gory detail, and I've never looked up the detailed paper where Friedman actually goes into the details here. Maybe I will at some point, but it's not that necessary to get the basic idea, and that's all I want to convey here. Okay, so let's start with the triple. We'll just leave one of those branches dead because we can't extend everything. Okay, and then we'll binary this guy off, and we'll binary this guy off. Okay, That's legal because this triple, even though there's 3 things here and there's 4 things here, this is really special. This is 3 things that immediately go to a common ancestor. That just doesn't happen down here. So it's not too hard to show that that's legal at this stage. Okay. Now, I couldn't just binary all these guys off. Well, of course, I can't spawn every one of these guys off ever. And so I'm going to have to kill one of them. So, and they're all symmetrical, so I'll kill this guy. Okay. And then I'm going to just spawn this guy once. And let's try and binary these guys off. Ooh, I shouldn't have ridden it so far to the edge. It's going to be a little bit tight with the room here. That's okay. Okay. So, let's see. I claim this is still legal. Okay. So, don't really have to worry about these guys mapping down, just because the triples are so special. You can check that if you want. Okay, so these 4, and in fact, actually, it's not too hard to check that this guy has to be fixed. So I'm going to box anything that actually has to go to itself. The root has to go to itself. This guy is very special because it's the lone guy in a triple, and you can show that that can't move. These guys could hypothetically switch, but if this guy goes to here, all of its descendants have got to fit into here, and there's not enough room. Okay, so they can't switch with each other. They could slide down in theory. Okay, but let's look at this guy. If this guy tries to slide down, its descendants, its 2 descendants, have got to slide down further, and there's not any room. So this guy has to be fixed right where it is. Okay. And now this guy, that means this guy, the only thing it could do is slide down, but we'll see that it really can't do that. Okay. Okay, so now what about these 4, the front rank of t less than or equal to 2? That's what we got to worry about at this stage. Could these guys go into these 5? Actually, after all, there's 5 options that it could go into. Okay. But if this guy is fixed, all of its descendants have to go to descendants of this guy. So this branch, this whole branch stays in itself. It can maybe maneuver around itself and slide down in itself, but it can't go over here. It can't take advantage of these guys. That's a big deal. Okay. So in particular, these 2 in the front rank of t less than or equal to 2, they only have one place to go, and so we're screwed. Okay. So which is a good thing. Okay. There's no match at this stage. Okay. Now, gosh, I really should have. Let me redraw that more closer to the middle. Okay, so at that stage we're good. And I claim we can extend it a bit further at the very least. Okay, so let me just go ahead, not be so silly, and start in the middle. Okay, so there's our 2, and I'll just put this way over at the edge because we don't need it anyway. Okay, and then this guy is going to be binaried off, but to be honest, that's not going to do much either. And that's just going to go down and die. Okay. And then this guy, binaries twice. Okay, that's binaries. And then these guys both binary. Okay, let me just check with my cheat sheet here. Okay, so that's what we had before. Okay. Now, I claim we can binary all those guys off, actually, which is pretty unusual. You don't want to kind of repeat the same thing over and over again in general, because then you're going to have a match. But if I check correctly, and by all means check me on this, and I'll redo the video if it's not quite right. Even if I binary all these guys off, I'm still okay, because this guy, remember, these guys were fixed. This guy's got to go somewhere, and it can't go over here, because it's got to go to a center of this guy. So just the fact that it doesn't have anything, that I've just killed it, basically means I kind of carte blanche to do something, whatever I want at this level, as long as it doesn't screw me up at the next level, which it could. Okay, so that's why I'm now getting a lot of freedom to create a lot of wiggle room. And that's, I think, the key here, is that the triple allowed me to do some binary stuff, and then selectively killing some stuff off in one branch has given me a pretty good head start in terms of how much space I have. Because one observation is that, like here, if I wanted to continue, this guy, this is just the earlier drawing of the same guy. If I wanted to continue this, I could very easily just continue it where I have, instead of 5 things, 4, and then 3, and then 2, and then 1, and at each stage, just because I have less room to map into, I'm not going to be able to have a match. But that's an obviously losing strategy very, very quickly. Okay, so what I've got to do is have a strategy where I can keep spawning part of the thing, but then kind of selectively killing other parts so that I get trapped into not being able to have a match, or which is a good kind of trap. I trap little parts of it so that I can't have matches, so I can continue without a match, if you know what I mean. Okay, so that's legal, I claim. Now, if you just did everybody binary here, then you'd be able to put in sort of part of it, put this whole binary that we've got here into, like, if I put an entire binary tree here, it would be embedded into here. So I need to, I think I can get away with just doing all but a binary tree here. So remember, what I was just saying, if I had a binary here as well, then an inf-preserving embedding would be fix all this stuff, and then take all this stuff, which is a binary tree of rank 1, 2, 3, 4, I guess 0, 1, 2, 3, really. And I just slide that and put it into here. And that's exactly an inf-preserving embedding. But I made sure that this was not a full binary tree. Okay. And then here, I'm going to do a similar kind of thing. I'm going to binary part of it, but kind of hack part of it off so it's not the same. And then I'm going to just have this guy go down and then kill this guy. So I'm kind of strategically having a variation from no descendants to a single descendant in some places to 2 descendants in some places. So you can check, and by all means, let me know if I made a miscalculation. But I believe this is gets us at least down to this level with a lot of nodes still alive, a lot of wiggle room to do this combined strategy of sometimes spawn into 2, sometimes continue, sometimes die. And this, I hope it's enough to give you the idea that now we're finally getting to a stage where, okay, I think we have some sort of strategy that's going to continue for a while. And this is where it gets interesting to think about. It's like, oh, okay, I don't think it's implausible to look at this and say, okay, I've broken the logjam, I figured this out. I can make this into a systematic strategy, an algorithm, a never-fail algorithm for selectively pruning and spawning. And I'm just going to keep going merrily on my way and never have a match. Well, that's the big theorem, is you can't do that. Is you can't go forever and not have a match. And it's a bit like, I think of it as a bit like the Gerstein sequence again. And especially there's this interpretation of the Gerstein sequence in terms of what's called a Hydra game, which is very similar to this, that we're sprouting we're sprouting heads of the Hydra. We're cutting off heads of the Hydra at various stages and sprouting them. And just because of the exact rules of the game, it turns out that no, you can't go on forever, but it takes a long time for it to catch up with you. That the sprouting seems to be proliferating. Oh, great, that's wonderful. We've got a lot of freedom to create more and more and more levels, but eventually a match has to catch up with you. Beyond that, I am not really qualified to say exactly more intuition about, why does a match have to catch up with you. If lots of people request it, then maybe I'll become an expert with some effort on things like Kruskal's tree theorem. Okay, so all we need to be convinced of is that it's plausible that TR of 3 might well be a big number, and that to know it's finite at all is a big theorem. And then where the hard work comes in is Friedman, and he doesn't say much, at least in the article that I was looking at, specifically about exactly TR of 3 and how big that is. But if we look at the function TR of k, the claim is that is a fast-growing function. And boy, is it a fast-growing function. Okay, so remember our hierarchy of fast-growing functions. We've got the standard fast-growing hierarchy. We've got f1, of n is just like 2n. f2 of n is 2 to the n times n, just the particular hierarchy that I've used. Okay, and then we get things that we were talking about when we were investigating the n of k function, the sequence function. F omega of n is f sub n of n. We diagonalize over all this family of functions, and then we start really cranking. We look at like f omega squared of n. We did some cool ordinal arithmetic. We get up to like f epsilon naught. Okay, and then we keep going. We look, we do things like, then the real fun with ordinals began. We had the Veblen hierarchy. We had like f phi sub 2 of, what do I want to say, like phi sub 2 of 3 or something like that, of n. We got these Veblen functions. Okay, so the idea again was to use the clever kind of recursion and diagonalization ideas, repeated recursion and diagonalization, and then recurse and diagonalize and over and over and over again, that built these guys in the first place out of sort of normal mortal infinite ordinals. We use that idea to create the infinite ordinals in the first place and use this as the subscripts to describe the recursion procedure to create the function and then apply n. Okay? The point, the real reason I wanted to go in all these videos and talk about the tree function is that it goes beyond even that, which I find pretty amazing for a fairly simple, the answer of a fairly simple problem. If you just get a little bit of background in graph theory and trees, you can understand the statement of this puzzle. And the claim, or the theorem, this is due to Friedman, is that TR of k grows faster. If you remember a few videos ago, the endpoint for the kind of that normal Veblen process, Veblen can be made more complicated, but for the normal one, it was this fancy ordinal called gamma naught, and this grows faster than f gamma naught of k. That was the state of the art a few videos ago for a fast-growing function. And, it really takes a whole bunch of technology to even describe how to create this function, and then to really figure out, to really get any intuition at all for how fast this thing grows is, almost impossible to get what most people would consider honest-to-God intuition. It is incredibly fast-growing. And we've found a real reason from a fairly basic graph theory problem, which I don't think would be that inconceivable to turn into, you could slip this into a textbook on a computer science, the practical computer science problems of, how do you organize information in a data structure, or how do you build the internet and you have this tree of different servers, feeding servers or something like that. You could sneak that problem verbatim into that textbook and then ask them, okay, so what do you think, what's TR of 9? And it would be ridiculous how big the answer is to that thing. He says that to describe the growth rate of this, it's not, you have to go to what are called ordinal collapsing functions. I've mentioned that very briefly before, and that's a possible direction I could go. I'd have to learn more about those. I've looked at them, but I'd really have to think about it. It's a way to use cardinals, uncountable cardinals, which are way beyond the kinds of ordinals we've talked about, to create new countable ordinals to label the f's. It's pretty sophisticated stuff. You have to use that kind of technology to talk about what really the replacement is for gamma naught. It's strictly bigger, significantly bigger than gamma naught, this huge guy. And one thing, just to finish up, I got almost about 20 minutes. What he says is he has a conjecture, and I think it's based on a lot of good stuff. I don't think it's really too much of a debatable conjecture. What he says is, what he's interested in really is the foundations of mathematics and proof theory, because this all relates to what he's most interested in is not the fast-growing functions. It's what kind of fragment of modern mathematics would you need to prove theorems like Kruskal's theorem and the variations of the Kruskal's theorem. And what would you even need to use? So there's two questions. What would you need to use to show that TR of k is finite for every k? Using the full power of modern mathematics and set theory, which is a pretty high-powered version by the standards of foundations of mathematics, you can prove that this is finite for all k. But if you take away some of the power, then it becomes impossible. And the fact that this is such a fast-growing function says you need a fairly substantial fragment of the full power of modern mathematics to prove that this even is finite for all k. Now, to prove that TR of 9 is finite, you shouldn't need, and you don't need, any significant big fragment of modern mathematics. You need a very small fragment. However, because it's just one single statement, you can actually go ahead and just list all the darn trees and check them and say, yeah, that's okay, that's still okay, that's still okay, and then just come to the dead end. And just like what we did with our, labeling of all these different trees. You could do it brute force, but oh my God, will it take you a long time. And what he conjectures is that if you use not the full power of modern mathematics, but a fairly standard fragment that people like to think about as being a very constructive and explicit version of the foundations of mathematics, he conjectures that proving that this is a finite number, that it's, in other words, that it exists as a finite number, that there really is, if you give yourself 9 branchings each time, that it really does dead end, that the minimal possible proof that you could write down requires, I think his conjecture is, at least like 2 5 up arrows 5 symbols. No matter how clever, greater than. No matter how clever you were, if you don't allow yourself set theory type proof techniques and sort of non-constructive proof techniques, that if you even tried to write down, if anybody ever wrote down a proof that even this one example exists as a finite number, you would need this ridiculously, this is by the standards of like, I wrote a book with this many letters in it. That is a ridiculously huge number. It's not as big as this number, but it's interesting that to even prove this big number exists with certain technology in mathematics, you've got to use that many symbols. That's pretty funky. Okay, so this is the main punchline I wanted to get across, is we've found a very explicit problem that leads to a growth rate that's not just fast, that's not just incredibly fast, it's faster than the incredibly, incredibly fast functions we were talking about before. So that's where I'm going to stop for now. There's other directions we could go later, but that's what I wanted to say on this part of these videos.